Okay, so today, I guess, is lecture number 7 for our class on distributed energy resources. I just wanted to go over a little bit of logistical information before we dig in to the lecture for today. So homework number 3 is not yet posted, but it will be posted probably by this evening. So I know that you guys are still working on homework number 2 on batteries and EVs, but the next homework will come up. So homeworks are kind of coming pretty fast and furious now. We're in this routine where every week you guys have a new assignment and it takes a significant amount of time to work through. So I encourage you guys to work with friends, take advantage of office hours and things like that if you get stuck on problems. But that pace will slow down. I mentioned this previously, but we'll kind of shift gears after. Okay, we'll get through sort of the modeling section, the modeling unit of the class, and then we will have a midterm exam. And then after that, homework will kind of slow down over spring break. And you'll probably either have one or maybe 2 homework assignments kind of in the post-spring break period, the second half of the class. And the idea is that we're sort of ramping down work on the homework and ramping up work on the class project in that second half of the class. So where we're at, we'll wrap up, I guess, depending on how I manage time today, we'll probably wrap up the buildings section. Then we'll get into heating, ventilation, and air conditioning equipment. Just one lecture on that. We'll talk about thermal energy storage and water heating. And then we'll do a lecture on solar, focusing on solar photovoltaics, but we'll get into some other aspects of solar energy as well. And then we will do kind of a summary, a roundup of this first unit. And then we'll probably have, I think we're going to squeeze 2 guest lectures into one day. And last semester, we had a few guest lectures. This semester, we'll probably do 2 or 3 as well. But I think that these guest lectures will be on kind of residential buildings and either renovating them to be sort of energy efficient or new build residential buildings and the sort of solar and batteries and EV charging and the kind of problems that you might encounter with new construction. So I think we'll have a renovation and a new build for residential in this guest lecture here. And then we will have basically project pitch presentations on these 2 days. And these will be roughly 5-minute presentations where you just kind of say, here's the broad topic that we're interested in. Here's a little bit of related literature that we've read about on this topic. And here's what we think our secret sauce is going to be, or the angle that we want to attack from. So with that in mind, we are trying to build you guys up gradually to kind of get you started on the project. So you should already have filled out your interest in a spreadsheet. I think almost everyone did this on homework 1. There will be another, like, I don't know, small point problem on homework number 3, which is basically to write down the members of your team and then the broad topic or topics that you guys are interested in. So you don't have to have everything specified at this point, but you should know I'm working with these 2 or 3 people and we're going to talk about solar, or we're going to work on batteries, something like this. And then we will ask you guys basically to do a little bit of reading. These could be reading, technical reports from companies or government laboratories. It could be reading academic literature to get a sense for kind of what people do within the domain that you want to work on. And then that'll build up. Basically, you should have the content that you need to pitch your ideas. And we'll do a little bit of Q&A basically to kind of clarify and pin down a little bit more specifically topics that you guys present on. So does that workflow sort of make sense? I will say that the second half of the semester is much more up in the air right now. These are all things that I think are pretty firmly organized and more or less being repeated from last year. But the second half of the semester will add some different content, different format and stuff. Any questions about that kind of logistical stuff before we dig in? Yes. Yeah, we will do the buildings part 2 content today. Oh, did I not put them online? Okay, I think I can probably do that. Actually, it's going to take more than a few minutes. So I'm going to ask, maybe you can just take notes on blank paper. But sorry, and thank you for the reminder. I'll be sure to put them up after class, and then I'll put up the next lecture for Thursday as well. Thanks. All right, so last time we did our first lecture on thermal modeling of buildings. So we talked about basically what goes into true sort of first principles physical modeling of buildings, why that's pretty hard and maybe not super well suited to problems and kind of designing and operating DERs. Then we talked about a simpler approach called thermal circuit modeling. which is a little bit easier and leads to kind of linear and low dimensional equations that we can embed into things like optimization routines to help us with sizing decisions, operational decisions, and things like that. So then we talked, after specifying kind of the forms of those equations, we talked about how to find the numbers for the parameters that show up in those models. And one of them was the thermal capacitance, C, basically the energy storage potential of or capacity of different things, air, building materials, and so forth. And then we talked about a parameter called R, which is basically the overall thermal resistance between the indoor environment and the outdoor environment, typically. And we talked about one way so far to kind of come at specifying the numerical value of this parameter R. Is this distracting with the door open? Would you prefer I close it? Yeah, we'll just let you guys go.
Yeah, it's probably the same level of distracting. If we're tired, as it is if we can hear them, but we won't know if we're tired, so it'll be less distracting.
Yeah, be very, yeah. People were joking about how the CO2 levels seem to get kind of high in this classroom because there's not enough ventilation and people get sleepy by the end of class, which I think is a really nice way of saying, no, professor, it's not you. We swear it's not your boring lectures. We'll see. Now you guys have no excuse, exactly. Anyway, okay, so this was the summary of that kind of data-driven, look at sort of historical weather data that shows up in the form of heating degree days or cooling degree days, and kind of combine that with energy data from, say, utility bills from a building, and figure out a way to basically back out what the value of this R should be. Okay, so we're going to come at this question of getting the parameter R, which, by the way, is a very influential parameter in these models. It essentially determines our estimates of how much energy we think a building will need for things like heating and cooling. So we'll talk about another way to come at that parameter, basically using more kind of physical intuition and material properties, things like this, rather than using energy bills and weather data. And I think if you wanted to be really precise and careful about specifying that parameter, you might do both and see how well they agree. And if they agree, you get some confidence that your estimate is pretty accurate. Okay, so here is basically an illustration of the various pathways for heat to flow in a thermal circuit between the indoor environment. So here, temperature T, you can think of that as the air temperature in this room, the thing that thermostat on the wall is measuring. And then theta could be a generic boundary temperature. This could be, very often, it would just be the outdoor air temperature. But as we learned last lecture, you can also specify kind of a combined boundary temperature that'll be a weighted average of various things, like maybe the temperature of the room next door and the temperature outside, something like this. So the first pathway here, the top pathway, has to do with heat transfer through the roof. So this would just be the horizontal surface above me. There could be conduction, basically, from the air in this room through the ceiling and into the outdoors. And then the middle pathway here would have to do basically with the vertical surfaces, the walls and windows. So here R, the subscript, means roof, and W means basically wall and window. And then there's another pathway here that has to do with direct mass transfer of air between the indoors and the outdoors. So basically, things like windows and walls are not perfectly sealed. So there's a little bit of air leakage between the inside and the outside around something like a window frame or a door frame. And we can associate essentially an R, a thermal resistance, with that pathway for heat transfer as well. So here in these equations, U is what's called a thermal transmittance in units of kilowatts per degree per square meter. So that has to do with the surface area, the vertical surface area of a wall, for example. And then A is surface area. M dot, this is in units of kilograms per second. So this is the mass flow rate of air between the indoors and the outdoors. And CP here is the specific heat of air at constant pressure. And this is a value that you can look up. Just Google or something. Okay, so here is what a typical wall assembly kind of looks like. So if you ripped off, from your apartment, if you ripped off the drywall and plaster and stuff that's on the interior surface, you might see something that looked kind of like this. So these vertical things here are studs. They're typically 2x4s or 2x6s. So that either 4 or 6 dimension is basically how deep they are, what the dimension here between the indoors and the outdoors is. And this is one way to get at sort of how well insulated a home is likely to be. if it's framed with 2x6s, it's going to have thicker walls and more insulation than a house that's framed with 2x4s, for example. And then you can see here, there are some outlets and things like this. There's electrical stuff, so we'd be able to plug things in there, window assembly, and then you can see the roof up here as well. So basically there can be effects called thermal bridging, basically. So heat transfer through insulation is pretty slow. Insulation like the stuff that's pictured here is, I think this is rock wool, which is a very good insulator. But heat transfer is actually more quickly through wood. So actually, if you wanted to be really detailed about how you modeled the sort of thermal resistance of this wall, you could get into kind of the parallel pathways and the thermal bridging effects between the wood and the insulation. Okay. So let's talk about kind of what the U and therefore the R values look like for different materials. So the thermal transmittances, and this is the thing U that shows up in these equations here, these values for what the thermal resistances in the circuit are. So typical values of thermal transmittances for a window with a triple pane window might be on the order of 1. And note the units here are watts per degree square meter, so not kilowatts. So typically you would convert these to kW before using them in a formula and then plugging them into your model. So thermal transmittance is low for something like a triple pane window, and then for a single pane window, it's significantly higher. So this tells you basically you get about 5x the heat transfer through a single pane window that you would get through a triple pane window. And this is basically why triple pane windows are more expensive, because they can save you money on energy bills over time. And then for opaque walls, so things like the overall wall assembly, kind of the average, including both the wood framing, but also the insulation in between the studs there, might be on the order of 0.2 to 0.8. So better even than a triple pane window, but for a not great insulated wall, you might actually see a U value that's similar to what you would see for a good triple pane window. And then for roofs, typically the upper bound here is a little bit lower. So usually attics and things like that it's not highly, I don't know, valuable space, I guess. So typically you can put a big thickness of insulation up in an attic. And for that reason, you typically have kind of higher resistance to, or therefore a lower thermal transmittance. But these things basically they come from the geometry and the thermophysical properties of materials that we use to build these things. So how conductive is glass, for example. And then in order to look at the sort of overall R or U value of an assembly like this, we'd note that we have parallel heat transfer pathways, for example, between the window and all this opaque surface here. So the overall thermal transmittance for the wall assembly, including the window and the insulated wall portion, would be a weighted average between the window U value and the wall U value. And it's weighted by what's called the, I guess, lambda here, the wall to window ratio. So I'll show some pictures of what this looks like in a sec, but a typical value of this lambda, the weight, and that shows up in this weighted average formula or this mixture formula, is typically between 10 and 30%. So if you look at this wall and you try to eyeball the area of this to the area of the entire wall, you might get 20, 25%, something like that. And that's fairly typical for most buildings. So if you plug in these numbers, typical values for windows, typical values for walls, typical values for the wall to window ratio, you might get on the order of 1 for the kind of overall U, the overall thermal transmittance of the wall. And here are just some sketches of what that parameter lambda looks like. So 0% lambda would be completely opaque. And then as we get closer and closer to a complete window wall, we might get close to 70 or 80%. Questions about this so far? Okay, so that was kind of one class of parameter that showed up in the that sort of parallel 3 resistance circuit that I showed. Another is the wall areas. So let us talk about that. So here we're going to assume a building that has kind of a rectangular footprint, basically a shoebox shape building. Not all buildings are shoeboxes, of course. Many have much more interesting geometries, but this is kind of a reasonable approximation for a decent number of buildings. So the aspect ratio of the floor here is basically the ratio of this wall length to this wall length. Right. So we call that alpha. And then the total floor area would just be, well, if we think of the floor area of one floor, it would be just length times width of this rectangle. So alpha L times L. So that'd be alpha L squared. And then we have n floors. So the total floor area would be just n alpha L squared here. And we can solve that for L so that we can later basically remove L from the next formula here for the total wall area that shows up. But the overall vertical wall area, so this is including both the opaque walls and also the windows that are on the vertical surfaces. So maybe a better subscript here would be V for vertical rather than W. But anyway, that ends up being 2 times the quantity 1 plus alpha times NLH. So where does that come from? Well, over here, this wall would have, let's see, a width of alpha L and a height of H. So that gives us alpha LH. There are 2 of those. So that's where the 2 alpha LH comes from. Over here, we have no alpha. We just have L, H, and there are n of those as well. So I guess that's where the 2 n LH comes from. And there are n floors. That's where we get the factor of n. Okay, so now we can use this formula for L that we got previously and plug it in for L here. And we get this kind of long-looking formula for the overall wall vertical area. And then the roof area is fairly simple. So that's just the floor area here. If AF is the total floor area, including all n stories, it would be the total floor area divided by the number of stories. So this formula here, we can simplify significantly using this approximation. So we have a 1 plus alpha here. We also have a square root of alpha in the denominator over here. And if you plot that as a function of alpha, the aspect ratio. So if alpha is really small, we have a really kind of long, skinny building. If alpha is 1, we have a square footprint. And then as alpha gets large, again, we have a long, skinny building, but in kind of the other dimension. So anyway, as we're close to 1 here, for alpha exactly equal to 1, this thing is exactly equal to 2. But even if alpha is 0.5, or you can kind of keep going out and it has more or less a symmetrical shape, kind of returning back up, kind of like a quadratic. As alpha gets close to 1.5, it might again get up to like 2.1 or so. But basically, for the values of alpha that we are interested in, this whole expression here roughly can be replaced just by 2. So that tells us that the wall area and stuff like that is not very sensitive to the aspect ratio. So this is a reasonable approximation of this larger, more precise formula. All right, so that kind of gets us all we need, the U and the A, for 2 of the heat transfer pathways that we talked about, through the vertical surfaces and through the roof. And the last important one that we talked about was basically infiltration of outdoor air, so direct mass transfer of outdoor air inside of the building. So here we have just a simple sketch of the building, and we can do essentially a mass balance and an energy balance on this thing. So we have a mass flow rate m dot coming in, assuming the building is in steady state, meaning we're not accumulating more air, we're not like blowing up a balloon inside of the building, then the mass flow rate coming out of it would be the same m dot. And we would have outdoor air temperature theta for the inlet air, and then as the air basically is displaced, indoor air is displaced by outdoor air, the air that goes back outside would have a temperature T that's equal to the indoor temperature. Okay. So under this assumption of steady state operation, we have the same m dot in and m dot out. And so we get that the overall rate of heat transfer that's associated with the mass transfer of air is just m dot times the specific heat of air times the temperature difference delta T. And this comes, like for folks who took thermo recently, this comes from using the ideal gas model and understanding what enthalpy changes for air are and how they relate to the mass flow and the specific heat. Or rather, the specific heat and the temperature. Okay. Let's see. How do we get the m dot? Well, m dot here can be expressed as a thing called nu, which is called the air change rate. And this is a kind of a widely used in the heating and cooling and ventilation industry. It's widely used to basically describe how much ventilation air a space would need. So if you're somewhere like a hospital where keeping concentration of pathogens super duper low is really important, or other spaces like laboratories might also need to be super clean in order to avoid dust and other contamination. So there you might have really high air change rates, maybe on the order of 10, 20, 30, something like that. For a space like this, per changes per hour. For a space like this, we might have kind of on the order of 1, maybe half of an air change per hour. And so what that means, basically, 1 air change is basically filling the entire volume of space with outdoor air, fresh air, 1 time. So, okay, so where does this come from? So air change rate, rho here is the density of air, and then the floor area times the height, well, that is just the volume of the space. So rho times the volume, that gives you, I guess, the total mass of air. And then this nu here has units of 1 over time. So when you multiply that per hour times the mass, you get basically mass flow per hour. Okay, so that tells us what the MDOT, a way to back up what the MDOT is. So you specify nu, we know what the density of air is. You can find the floor area of the space quite easily. Specify a ceiling height. You could imagine this is, I don't know, 4 meters or something like that in this room. So you can kind of easily specify all these things, and that gives you a rough kind of time average mass flow rate. And that's what shows up, let's see, here in the expression for this resistance here. So we've talked about how to specify all the U's, all the A's, and how to find the MDOT. CP is something we can just look up. So with all of those things, we can estimate the overall thermal resistance between the indoor and the outdoor air as 1 over basically the sum of all these things. And that just comes from the formula that you probably learned in a circuits class at some point, or in an E&M class for the overall resistance of 3 resistors in parallel. Okay, so to summarize all of that, I basically took that stuff and plugged in plausible values for kind of each of the physical constants that shows up. And we get a way to estimate the overall thermal resistance, or actually here to estimate its reciprocal 1 over R. So you can plug in these numerical ranges. You could imagine calling like MATLAB or Python code where you would call a random number generator, and you might pull it from each of these ranges. And then you multiply by the things that are easy to figure out about the building, like what is the overall floor area of the building? What is the typical ceiling height for the building? How many stories are there in the building? Kind of simple geometric information. And so we plug all that stuff in here, and we get an estimate for 1 over R. Take the reciprocal, and you've got the estimate of R. So if we plug in numbers here for a typical house, so I think in that second half of the semester, when the pace of homework and stuff slows down a little bit, we won't spend quite as much time going through tons of equations in class, and we will, in at least 1 class, probably 2, we will take tours of nearby energy facilities. So one of them is a test house that my graduate students and I do a bunch of experiments in, called the DC Nanogrid House, which is just kind of across the road from here. So that house is about 200 square meters. This ends up being, I think, about 22 or 2,300 square feet. And it has 2 stories, and the ceiling height is, I don't know, about 3 meters, maybe 10 feet, something like that. So if you plug those numbers in here and you crunch all of this in a calculator, you get a value of around 2.5 degrees Celsius per kW for the overall thermal resistance between the indoors and the outdoors. And that ends up being fairly close, actually, to what we observe when we fit real data in our testings. All right, so then the last thing that shows up in the thermal circuit model that we wrote down, we have an R parameter, we have a C parameter, and then we have a time series that we call QE, which I call the exogenous thermal power, but you could also call it the internal heat gains, or you could call it a disturbance term, basically the thing in the equations that we can't control. So that thing, QE, can be decomposed into 3 parts. So one of them is heat gain from the sun, sunlight coming in through the windows right now. Another would be the plugged in stuff, so projector lights and so forth. And then a third would be body heat. So each of our bodies typically gives off around 100 watts, more or less continuously. But also things like cooking, burning wood and fireplaces and stuff like that. So of these, the second one is often measured. So if you just look at the total electricity consumption in a house, that's a reasonably good way to estimate kind of the heat that's being given off by devices. So most of the electricity that goes into a house ends up getting dissipated as waste heat within a house or an office or whatever it might be. And here's a rough expression for basically how to fit that. And this comes from survey data from a US government office called the Energy Information Administration, I guess. And then again, about 100 watts per body for this other thing. It's kind of a reasonable estimate. And you may remember that from kind of the first way that I presented, the weather data and utility bill data of estimating the thermal resistance, we also got this interesting formula that said that on average over time, the value of QE here should be about delta divided by R. And we talked about lots of ways to estimate R, and delta, again, is this number. It basically says, what does the indoor-outdoor temperature difference have to be for basically before you have any demand for heating from the house. So this might be on the order of, kind of 4 to 10, something like that, degrees Celsius. So after basically coming up with ways to estimate all of this stuff, you can sanity check your estimate by plugging it in and comparing it to something that you have in your mind for delta, and then whatever you calculated for R. So it's kind of an overall consistency check on the model. Okay, so that leaves number 1. And in our class on solar energy, we will talk about precise methods to calculate how much heat is gained from sunlight. And it has to do with, not only what are the area of the windows, but what direction are they facing. So the amount of sunlight we're getting in from these windows is not very much, but those are getting direct sunlight, and so they're getting more heat through them. It also has to do with what's called the solar heat gain coefficient of the window. So some windows are treated to reflect a lot of sunlight. And in particular, the infrared and thermal portions of solar radiation, some are not, and so on. So there can also be shading devices and things like that. So it gets fairly complicated to do these kind of more precise calculations. But here is a rough formula that you can use in order to estimate, ballpark what the energy you would get through all the windows in a building would be. So here it's kind of this number in this particular range. We'll talk a little bit more about where these numbers come from, times C, this thing that we call the solar heat gain coefficient, which is the fraction of the basically energy content from incident sunlight that actually makes it through the window into the building rather than being reflected. And then this thing that shows, so N is the number of stories, H is the height per story, lambda is the wall to window, the window to wall ratio that we talked about. And then AF, this is the total floor area for the building. And then this thing here, S, is a new thing that I'm just introducing here, but this is called the total solar irradiance as measured on a horizontal surface. So there are devices to measure this. There's a pyranometer and a pyrheliometer. We will talk a little bit about those and how you would measure this if you wanted to. But the basic point is that this is the sort of thing that you can download from a weather service because it's something that can be measured. So you can take that data and then you can plug it into this formula and you will get a rough estimate of what the heat gain from the sun is at any particular time as a function of that solar measurement. And then you may also want to simulate, for example, in summer when you're in air conditioning mode on a hot day, if sun is beating into a building through a south-facing window, people might close the blinds, right? So that would change essentially this fraction, C, of the sunlight that actually ends up entering the space. So you might say on summer afternoons, this C should be small. It should be 0.2 or something like that. Whereas on a winter afternoon, when it's kind of chilly and you're heating, you might really welcome that nice sunlight coming through a south-facing window like we're getting today. And so we might open all the shades and let sunlight in. And that might mean increasing C to 0.7 or 0.8, something like that. Also, foliage from trees is going to vary seasonally, right? So very often you have a southern-facing window that might have a deciduous tree by it that has a lot of sunlight entering it in winter. But in summer, when that tree is in full foliage, it probably wouldn't get very much. It's going to be shaded most of the time. And then, yeah, we will talk much more about this when we get to our lecture on solar energy. Okay, so questions about that last kind of chunk of buildings part 1 material? Okay, I think I want to shift gears at this point and just talk about the homework assignment really briefly, and then we will jump into the second lecture. Okay, so this is what homework 3 looks like. Again, we will put this up online by this evening. I know you guys are currently working on homework 2. But we've changed the wording very slightly. So we said in the grading chunk, previously we used to say 0 points for a solution that's unreadable or missing, and then or 1 point for a serious attempt that's either not easy to read for the grader or it's not correct. And then full credit if your solution is both readable, pretty clear, and also either correct or close to correct. And we've changed that to no credit, half credit, and full credit. And then put here, just so you guys can like manage your time a little bit better, we put here essentially what percent of the overall score for this homework is each problem. So here, our first problem is 15%. We've now had problems kind of like this on the previous homeworks, but this is basically just a way to go from the continuous time differential equation to the discrete time dynamics here. So you've done that a couple of times. We're going to do it in the buildings context. This one, we will use kind of the weather and energy data method to come up with an estimate of R for a house in West Lafayette. 3 is it's fairly short calculations, but they're oriented toward this question of, is it cheaper to heat a building that is short and kind of wide, or a building that is tall and kind of narrow, assuming that the overall interior floor area is the same. So if you want a 2,000 square foot home, is it better to have a 2-story home or a 1-story home, for example, if what you care about is the heating and the cooling bills, rather than say, if your home looks nice. Most people, it's much more important. Anyway, so there's multiple parts here, and we kind of walk you through the calculation. And then by the end of this question, you should be able to say, at least, with respect to the assumptions that we've made in this problem, whether it's better from a heating bill perspective and a cooling bill perspective to have a short or a tall. And then there's a coding problem as well, and I will walk through briefly the code. And then there's just a little kind of final question here. Either you do it or you don't, but we just ask you to write down all the names of your teammates and then the topic or topics that your project or that your team wants to focus on. And then today's lecture, really, we will talk about the stuff that goes into these scripts here. So we'll simulate the operation of a thermostat that kind of turns off and on a piece of heating equipment periodically, and so on. So I think rather than going through that code right now, because it may not make that much sense before we've presented the material, I will jump over to the next lecture. Okay, so we're just kind of picking up right where we left off. So these slides talk about higher order thermal circuits. So we talked about 1C, basically first order thermal circuits that had one temperature state. That was kind of the last lecture, I guess, and a half now at this point. And then we'll talk about 2C and then general higher order NC models. And then we'll talk about how you simulate buildings. And in particular, simulating the thermal dynamics of the building requires having some information about how the heating and the cooling equipment is working. So we'll talk about at least 2 ways to operate or to simulate the operation of heating and cooling equipment. And then those simulations, that code, is what will go into the homework problem for next week. And then there's an analogy between buildings and batteries or thermal energy storage, thermal batteries. And we'll try to make that analogy clear in the last section here. We may not have time to get to that today. Okay, so the simplest higher order thermal circuit is a 2R, 2C circuit. I guess you can maybe think of a simpler one, but this is the simplest useful one, I guess I'll say. So here, this looks a lot like the 2R, 1C circuit that we showed last lecture, except here there is another capacitor in the circuit. So the previous circuit that we showed had one capacitance representing the heat storage capacity of the indoor air and like the shallow thermal mass, stuff that's usually close to the same temperature as the air. And then here we add in the second thermal capacitance, which represents the energy storage capacity of all the wall materials, kind of the deeper thermal mass. And then here we have coupling between the indoor air temperature and the mass temperature, but we do not have in this model coupling directly between the thermal mass and the outdoor air. And you could easily put another R in here, and then you would have a 3R, 2C circuit. And that's fine to do, although typically most of the thermal mass of a building is usually interior. So if you think of, there is thermal mass in kind of these cinder block exterior walls right here, but there's a lot more interior walls and floors and ceilings and stuff like that, and furniture and everything else. There's a lot more sort of mass and material interior to the building than there typically is in the building shell. Yes.
Just going back, but when you are thinking about that interior map, do you also sort of people inside the building?
So the question is, do you consider people when trying to, for example, if you wanted to calculate what this thermal mass is? Usually not, although I guess you could. I guess, yeah, you could assume how many people, and then you could just model people as water. Our bodies are mostly water, right? So I guess you could do that. Yeah, people typically don't in this field, but yes. Yeah, so does it matter? As long as we are modeling this thing over here, basically the body heat that's coming off of those people, does it matter if we model their thermal mass? I guess, so this thermal mass here, so if you think about how the dynamics of the circuit, if you think about how it would work, so basically we would heat up or cool down this mass by adjusting the indoor temperature. So this is like, if we made the indoor temperature 90 degrees Fahrenheit, eventually this thermal mass temperature would also become that same 90 degrees Fahrenheit. And our bodies have all sorts of temperature regulation capabilities, right? We have all sorts of biological control systems that make us sweat, and we would take off layers and things like that. So our bodies typically, are within a pretty narrow temperature range. So modeling them as sort of their temperature being driven by the air temperature of the space in this way, it's probably not the right physical model, I guess. That's an interesting suggestion. I hadn't really thought about it. If they're dead bodies, yeah, then sure, go ahead and model.
We've got their problems.
Yeah, if you're, yeah, probably go. I guess, what's that? If you're building a morgue, then maybe yeah, a morgue without air conditioning for the bodies. Anyway, this is getting morbid quickly. So anyway, you can write down basically by doing Kirchhoff's and Ohm's circuit laws, you can write down the governing equations for this circuit. And they look pretty similar to the equations that we wrote down for first order thermal circuits. But now we have a second equation that basically governs the evolution of the mass, the thermal mass temperature, in addition to the first equation that governs the dynamics of the indoor temperature. And we also have this additional term in the air temperature equation, which relates to the coupling, the thermal coupling between the air and the thermal mass. So if you think back to our lectures where we talked about how to do basically time discretization for higher order linear differential equations or dynamical systems, we had some steps basically, and I'm going to go through those in this example. So here we have the time derivative of our state vector, which would just be the temperatures of the air and the thermal mass, is the matrix A, and here's what that matrix looks like, times the state vector itself, plus a matrix B times the input signal, which here is composed of two pieces, one of which is the heat or the cooling that we deliberately deliver through the mechanical equipment, air conditioners, heaters, etc. And then the other one is this disturbance W, which here is composed of both the outdoor temperature divided by the resistance and this QE term, which is all the body heat, solar energy, etc. So you can look back at the governing equations here, which are written kind of as two coupled of the E's. You can look back at those and convince yourself that in matrix vector form, they satisfy this equation with these definitions. So it's probably a good exercise to do just to understand where these equations come from. And then looking back at the material on linear dynamical systems, we know that we can discretize this continuous time ODE system into a system of difference equations, basically discrete time dynamics equations, using the matrix exponential. So here, the discrete time matrix A is just E, the matrix exponential of the time step times A tilde here, which is this continuous time dynamics matrix. And then we get a formula for B as well. It involves the inverse of this matrix A tilde. And if you want to just do math for the sake of doing math, you can prove that the inverse of this matrix exists. So you find its determinant and things like that. Okay. So this is all kind of just repeat stuff from the first couple of lectures on math applied to this 2R2C whole circuit. Okay, so coming up with the parameter values for the additional, basically two new parameters that we've added, the mass capacitance Cm, and then the resistance between the air and the thermal mass. Okay, so roughly, and this is just super coarse, back of the envelope kind of stuff, but the thermal mass capacitance for a typical building might be about an order of magnitude larger than the thermal mass for the air and sort of the shallow stuff. So if you've already gone through the process of creating C, then you can multiply it by, order of 10, 12, something like that, to come up with an estimate of Cm. And if you want a sanity check on that, if you take the value of Cm that you calculate and you divide it by 0.3 in units of kilowatt hours per volume per temperature degree, that ends up being roughly the equivalent volume of pine that you would need in order to have that same kind of heat storage capacity. So you think like, oh, is it, way more pine than we could possibly fit in the building? Okay, then that's probably unrealistic. Is it like a marble of pine? Okay, that's probably also unrealistic. But is it, some fraction, some 20%, 10%, something like that of the overall volume of the building? Okay, well, then it's kind of plausible. Not that all the thermal mass inside of a building is pine. In this building, everything's made out of cinder blocks. So I guess, concrete would be a better thing to use. But you could do something similar by basically looking at physical properties of concrete. And then the coupling between the indoor air and the thermal mass is typically stronger. So there's usually not deliberate insulation between, for example, the air inside of a room and the thermal mass inside of interior walls. Not in the same way that there is insulation usually in the exterior walls of the building. So for that reason, the coupling strength is tighter, and that means that the thermal resistance is smaller. And if you look at, people have done studies of real buildings and try to fit these parameters in the past. And if you look at what usually you get, it's typically, divide by 5 or something like that as kind of a rough estimate of the coupling between the indoor air and the thermal mass. You could increase that. You can imagine all sorts of ways. If you blow a fan, you take the indoor air and you blow it over thermal mass deliberately, that would increase the coupling, so it would decrease R. You could put up insulation and that would increase R. So. Okay, so the 2R2C thermal circuit is kind of interesting, and it actually highlights kind of a mathematical move that people often use when analyzing dynamical systems, things that change over time and that have multiple states, multiple coupled states. So this is called, there's various things. Time scale separation is kind of the more mathematically precise language. Two timing is kind of the I don't know, catchier term in my mind. But the idea here is that the indoor temperature T, if you just look at data, so if we put a thermocouple deep inside of the wall, we measured that temperature, and then we compared it to the measurements of the thermostat, we would probably find that over the course of a day, the indoor temperature changes a lot and changes kind of quickly, depending on what the heating and cooling systems are doing, how much heat we're getting in through the windows, how occupied the room is, and that kind of stuff. Whereas the measurement of, deep in these cinder blocks probably would be very stable. It might show a little bit of change, but it might take hours for it to change a single degree. So for that reason, we kind of separate. We can say there are sort of two characteristic timescales. There's the fast scale associated with the air dynamics, and then there's a slow timescale associated with the thermal mass dynamics. So then we can make assumptions about the derivatives, basically, of the different state variables in these two different kind of limiting regimes. So if we look only at the fast timescale, we can model the thermal mass temperature as approximately constant. And then if we look, so maybe we're only looking at an hour or a 2-hour time span, and we'd say, yeah, the thermal mass temperature might change a little bit over that time span, but not very much. So we assume that it's negligible. And then over a slow time scale, so maybe we're looking at weeks or months, we might say the indoor temperature is approximately constant. And what we really care about is what's happening with that deep thermal mass temperature. So let's just take these assumptions for these two timescales and plug them in and see what happens mathematically in our 2R2C model. So if the thermal mass temperature is approximately constant, in our first governing equation, originally we had a Tm of T in here. So all we do is just take that and replace that with the constant, 20C, 21C, something like that. And then we're back basically to a 2R1C model, which we studied pretty exhaustively last lecture. So we can define an equivalent thermal resistance or an effective thermal resistance, an effective boundary temperature that ends up just being a weighted average of the thermal mass temperature and the outdoor temperature. And then we're back to our 1R, 1C model, which we already understand pretty fully. Okay, and then if we look at, again, maybe we're doing long, slow simulations, we care a lot about what's happening with the mass temperature. We can basically assume away the time derivative, assume that the indoor temperature is constant. And then we get basically just this one equation. And this actually is just literally directly transcribing the second equation that showed up kind of in the original governing equation system. So assuming this T is approximately constant over each time step, so we're not assuming that it doesn't change. This is what's called a quasi-steady state assumption. So we're allowing the indoor air temperature to change, but we assume that it's always approximately in a steady state. So its changes are modeled as basically instantaneous. So under that model, then we get these dynamics, a very simple, again, 1R, 1C type dynamics for the thermal mass temperature. And here's what this parameter A is. And then we get essentially an output equation. So the differential equation that we had with dt, the time derivative of the indoor temperature being non-zero, that differential equation under this quasi-steady state assumption becomes just an algebraic equation. So dt by dt here ends up being 0 in the original equation. And then we get essentially an output equation that tells us, based on what's happening with the indoor temperature, the outdoor temperature, and the thermal mass temperature, it tells us how much heating or cooling basically would be needed in this space. And then we can play similar games with larger, higher order thermal circuits. So if you wanted to come up with one model that talked about the coupled temperature dynamics of this entire building, which might have 100 rooms in it, you might have a 100-dimensional or a 200-dimensional model, where maybe we have a thermal mass and an air temperature associated with each room in the building. And then there would be coupling between them. So here is kind of a general form. If you look at the ith state, state I, so say the air temperature in room 12 or something, we can write it basically, the dynamics here, again, by doing a Kirchhoff circuit law balance, conservation of charge balance at this point here. If you do the math, you can write down this equation. So in these models of MR, NC, kind of arbitrary dimensional thermal circuits, typically you'd say node 0, you'd call it a boundary node, and this might be, for example, the outdoor temperature. So you wouldn't have a dynamical equation associated with the outdoor temperature, but it would show up as essentially a driving term in the right-hand sides of these differential equations. Okay. You can basically set R equal to infinity if there's no coupling between a zone I and a zone J, or 1 over R equal to 0. So this zone and then something, on a different floor on the opposite side of the building, there's no direct thermal coupling between those. So we could say, basically set that term equal to 0. And then if there's no controlled heating or cooling injected into a space, so for example, a hallway might not have radiators or vents in it, then that Q term could be 0. And then we can use the kind of linear dynamical systems approach to discretizing equations that we used for the 2R, 2C model. So the matrices are bigger, it's harder to write down all the components. There are many more parameters that enter into these large models, but conceptually, the process is the same as it was for the 2R, 2C case. Okay. So now we will get into basically the algorithms or the ways of basically simulating buildings that involve some information about how buildings are controlled, and specifically about how the heating and cooling equipment in buildings is controlled. So again, this is the coding problem that shows up in homework 3. So the simplest thing to simulate would be what we call perfect tracking control or perfect set point tracking control. So the idea there is that if you were to change the setting on the wall thermostat, the model underlying this approach to simulating buildings would say that the actual measured indoor air temperature basically perfectly tracks whatever we specify. And so then we can back out, for example, energy usage from that. So for a 1R, 1C model, how do we simulate perfect tracking control? Well, we have the discrete time dynamics. We know this parameter A, and we know R. And we talked about ways to basically come up with the things that make up this W, which is the outdoor temperature, and the heat gain from bodies and sun and stuff. So this model we have completely specified. And so we might just think, okay, if you have the current state tk, and you want to be able to simulate the evolution to a state t at time k+1, say 1 hour later, we can basically back out the heat or cooling that's required in order to drive the indoor air temperature from its current state tk to exactly the specified temperature set point at time k+1. So we make a change to the thermostat, we raise it by 5 degrees, and then this formula basically tells us exactly how much heat or cooling would be needed in the 1R1C model to deliver that temperature change. Okay, so this would basically give us a way, given the input data t hat, the temperature set points, you could say, well, how warm or cold do the people like it in the building? And then you could back out what's needed in order to exactly deliver that. And so that would be basically giving you a way to simulate all the building, its energy usage, temperature evolution, and so forth. And we could do that in a 1R1C case. We can also do it in a 2R2C or the general kind of NR-MC case. So here we again write down the discrete time dynamics. And then we say, well, what is needed to drive the indoor temperature from its current state to the desired state at the next time step. And then we just take the first equation here that shows up in this 2 by whatever system. And then we invert this or solve this equation for Q hat C, basically. So this, again, same form. It basically tells us as a function of the boundary conditions and the user specified temperature set point, it tells us how much energy would be needed for heating up. Okay, so that's probably the simplest way. It's maybe not that accurate because, so for example, if we're in heating mode and we took the set point over there, say it's at 72 Fahrenheit, and we dropped it to 65, the perfect tracking model would say that, at the next time step, 5 minutes from now or an hour from now, whatever it is, that it would become exactly 65 degrees in this room. Which is not really how the system would behave, because you'd probably need air conditioning in order to reduce the temperature in this room that quickly. So typically buildings are either in heating mode or they're in cooling mode. So even if we put that thermostat at 50 Fahrenheit, the building would not turn on its air conditioning system. I don't even know if there is air conditioning in this room. There probably is, but there must be, right? So actually, more likely what would happen is that we would have to kind of put in a lower limit for the amount of heat that can be supplied. So a negative value of QC, for example, would represent supplying cooling to the space. And we don't want to do that. That system is sort of disabled for the winter. So we'd say the lowest you can go for the heating is 0. You can't go negative, basically. So we could pick a value 0 on the lower end here. And then we also might put in an upper limit on how much heat we can deliver. So there's only so much heat that can come out of the radiators in the back of the room, for example. So if we raise that to 1,000,000 degrees Fahrenheit, we wouldn't be able to instantly deliver that. Yes, question. Yeah, so the question is, why do building operators typically disable the cooling system in the winter? I guess the answer is they don't always do that. So there are building types where actually, even on a really cold winter day, you can have like core zones, interior zones that have no like exterior windows or anything like that. They're only like an interior office at Herod, for example, might not. The grad student offices don't have windows, right? So, but they might have closed doors and they might have a bunch of computers and body heat and stuff like that. So there may be rooms inside of a big office building that still need cooling even on a really cold day. And so there you might leave on the air conditioning system for those rooms and use the heating system for other rooms. I think it's more antiquated buildings like this one, a little older, that typically would have this kind of binary operation thing. And I think I'm not exactly sure why. I think part of it is to save energy. It seems a little wasteful to be air conditioning over here and heating over there. Yeah, it's a good question. Sometimes you have like only one piece of equipment and you might have an air source heat pump that one piece of equipment that provides both heating and cooling. And you might have to like physically trip a switch or something in order to flip it. So there, again, this model of exclusion between heating and cooling, that makes sense. Good question. Any others? Anyway, so here basically when simulating a building, we could do basically the same move. We could calculate the amount of heat or cooling that would in theory be needed in order to exactly track the user set point. But then we would saturate, this is called a saturation curve, saturate the desired heat or cooling provision within some reasonable capacity limits. And so we get this roughly kind of S-shaped thing here. So say this is 0, we don't want to allow cooling. This Q hat that showed up from the previous equations, the amount of cooling that would be needed to exactly track the set point, maybe it's -5. We're way down here, and the blue curve here would actually just be at 0, rather than being down at -5. And similarly, if we raise the set point to 1 million, we would not be able to provide that much heating. The most we can provide is whatever we can push out of the radiators in the room. And so we would saturate above at Q max. Does this make sense? Okay. So the basic approach to simulating this near perfect set point tracking that includes saturation would be first use, say, this equation from the 1R1C or the 2R2C version, calculate sort of the desired or the sort of theoretical amount of heat or cooling that would be needed, and then run it through basically the saturation curve to clip it above or below into the appropriate range, and then take that and go back into the sort of true dynamic equation here. So plug it in for QC with the boundary W and so forth. And then the actual T K+1 that we get would not be exactly equal to the T hat. It would be something close to it, kind of as close as we could deliver given the capacity constraints. Another simple and really widely used control method for heating and cooling buildings is called thermostatic control. So thermal is like temperature, static is like no motion. So this is like keep the temperature steady, basically. Thermostatic control is used primarily in systems that have on-off kind of behavior. So rather than a variable speed piece of equipment that can kind of modulate its heating output or cooling output continuously, we're thinking of things that are controlled in a kind of bang-bang fashion. Either you turn the air conditioner off or you turn it all the way on. Okay, so to simulate that, suppose that we have in a dynamical system, we have an action variable that's either 0 or 1. It just indicates whether the heater is on or off. And we would specify a deadband here, and I'm using a lowercase Greek delta. This is not the same lowercase Greek delta that we used in the calculation of that thermal resistance R. So here, the value of delta typically would be ½ degree or 1 degree Celsius, something like that. Okay, so to do the simulation, we would say begin the value of this indicator, the on-off indicator, begin it at whatever it was previous. So if the heat was on, start with the heat on during kind of the next decision-making stage. And then we say if the temperature has risen above the set point plus this parameter delta, the half width of the what's called the dead band, if we're above that band of temperatures, okay, then turn off the heat. Conversely, if we are below that sort of dead band of temperatures, so the set point here might be, I don't know, in Fahrenheit 72, and the dead band might be 1 degree. So if we're below 71, okay, then it's too cold. So so turn on the heat. Okay, and then what do we do? Well, how do we translate into a simulation platform? So we would say we want to define the heat supply QC here. So that would be the minimum plus U times the difference between the min and the max. Usually, really almost always, this minimum here would be 0. And so this simplifies to just setting QC equal to U times Q max. So if the heat is on, you provide the maximum capacity. If the heat is off, you provide nothing, no heat. And then we increment K. We use our dynamics equation to update the indoor temperature and possibly other temperatures, thermal masses, and things like that. And then we just repeat the process. So you can embed this into a for loop in MATLAB or Python, and you can come up with a way to basically simulate the building. And this is pretty similar to the control logic that's used kind of in probably 80–90% of the buildings that you've ever been in. And here's what that would look like. So if we looked at the measurement that's coming off of that wall thermostat, so in the middle of this thing that we call the dead band, The middle of this would be T hat. I guess I didn't mark it here for whatever reason. But this is the number that you would put into the thermostat or your phone app for your Nest thermostat or whatever it might be. Here, we're showing an on period, okay? So the heat is on, we're raising the temperature inside. We get slightly above the dead band, and then we turn the heat off. And then we kind of slowly decay. The indoor temperature drops. Eventually, we get a little bit below the dead band. And then we hit this piece of logic here, which says, oh, it's too cold, turn on the heat. Bang, heat turns on, and we warm the indoor air back up. And then you would see this kind of sawtooth pattern. That's very typical of thermostatic control. Questions about this?
How would you sort of, you mentioned 89%, what would be, if we were to make this more complex or like try to, over engineer this, what would you do? How do you make this better?
Yeah, how do you make this better? Well, so I guess let me talk about some situations where you would see something other than thermostatic control. So one would be if you don't have like equipment that's either off or on. You might have equipment that has multiple stages. So for example, in one of our test houses, we have a heat pump that provides most of the heating, but it doesn't have enough capacity to keep the house warm, even on the very coldest days. So when it runs out of capacity, it turns on a second stage of heat, which is electric resistance heat, just a big hunk of metal that you can run current through to get heat out of it. So there you would need additional logic. It would have a similar flavor, a similar binary sort of flavor, but you would say, okay, if, the temperature is below, maybe there's a second level. So you're running this, and actually when the heat is on, rather than going up, you actually continue to drop. If you get below a second temperature threshold, you might turn on that second stage of heat. So again, quite simple, but a slight extension of this. And then there are multi-stage systems that have 3 or 4 different settings that a compressor can run at, for example. Another one would be if you have variable speed equipment. So a motor typically can either run on off, or else inverter driven motors can have kind of a continuous RPM range that they can operate through. So there, rather than using this kind of bang bang type control logic, you might use something called PID, proportional integral derivative control logic, which basically says the proportional, I'll just talk about the proportional thing there. What that says is, okay, you want the temperature to be at some specified T hat, say 72. So look at the error, the difference between the measurement and that desired level. And then as that error grows, the amount of heat that you supply also grows. It's like trying to drive the temperature back to the set point. And then you wouldn't have this kind of zigzag thing. You would have kind of a more smooth, it might look sort of sinusoidal, but it would look much, much smoother. And there, tuning those controllers can get much more difficult. Also, variable speed motors typically like to operate within a range. They don't like to operate at super low load. So they have kind of an on-off plus continuous flavor. So if you get into how like manufacturers actually tune those controllers and design them, it's actually quite complicated. So that would be another example, is variable speeds.
Right.
Yeah. And then like there's all sorts of other stuff. So if you're trying to do like grid services, you're trying to use the energy storage capacity of the building to like, do a buy low, sell high type of thing with respect to time varying energy prices, then you might use a very different form of control. But good question, thanks. Okay, so I'm going to go through an example, and this example probably will take the last 7 or 8 minutes of class. And this is basically the coding homework problem that shows up in your assignment next week. So let's do an example where we have a higher order thermal circuit, a 2R2C circuit in this case. And we'll talk about a physical example of a house. Again, this is kind of like our test house that's a couple blocks away from here. A 2-story house with a floor area of about 200 square meters, about 2,200 square feet. And we're simulating over 5 very cold days from, I guess it was a cold snap that we had a couple of years ago here. So this is the outdoor temperature in Celsius. You can see it's around freezing on the first day, a little warmer in the afternoon. And then just before Christmas, this cold snap happened over the holidays. The temperature dropped a lot to about -22°C, something like that, which is around -5, -10 Fahrenheit, something like that. So very cold. And then it stayed pretty cold, gradually got warmer over the subsequent days. And here, this thing I'm calling the exogenous thermal power. This is the QE. So this is kind of the mix of body heat, heat from electronics and stuff, and then solar heat. And so you can see that in the afternoons, there's some solar heat gain that we get, which correlates a little bit with it getting warmer outside. Okay, so this is simulation results from basically the perfect set point tracking control. So, and actually it's the perfect tracking, but with saturation. So we're not allowed to turn on air conditioning, for example. And we only have so much heat that we can supply. I guess about 14 kW of thermal energy is our maximum capacity. So, and then this is our set point. It's time varying. So we assume that people like a nice toasty house during the day, and then overnight they drop the temperature by, I guess, about 3 degrees Fahrenheit, roughly, 3 degrees Celsius, or roughly 6 degrees Fahrenheit. So you might go from, say, 73 during the day to 67 overnight. And then we look at basically how the black curve here, which is the indoor temperature, tracks the set point. And so you can see during times when we are at our capacity limit, when we're working basically the heat as hard as we can, we don't perfectly track the set point. So it doesn't exactly match the square wave. Instead, we have kind of a delayed temperature ascent, basically back up to the set point. And then if you look at what the thermal mass temperature is doing in these simulations, it's kind of doing this sawtooth thing that's more or less trying to track what the indoor temperature is doing. So if you imagine keeping the set point high and constant, rather than doing these overnight set point reductions, we would see kind of an exponential approach of the red curve to that incline. But then we drop the temperature overnight and we begin to see this kind of another exponential approach between the mass and the indoor. All right, so that is the sort of perfect tracking, but with saturation. And then, oh, sorry, this is the 2R2. This is a slightly different simulation than what you guys will do in your homework. I think your homework, you do this one, and then you do thermostatic control. So this kind of on-off control. But here, basically, I guess in these simulations, I'm comparing the exact 2R2C results to the results of simulation with the 1R1C models that we got from the two timing thing, where we assume either there's a fast time scale or there's a slow time scale, and we kind of neglect the other one. So this is if we look only at the fast time scale, and we assume that the thermal mass temperature is constant. So here the red line is just totally flat, and I chose to just keep it at basically the time average value of the indoor temperature. So if you look at the average of the black curve here, I guess it's equal to the red. And so you can see that compared to the exact, again, models are always mismatched from reality. There's really no such thing as an exact model. But if we assume that 2R2C is like our ground truth, we can ask how well do we approximate that ground truth under this kind of two timing assumption. So if we compare here what the graphs look like, I'll just flip back and forth between them. The air temperature dynamics look really similar. And the power profile also looks really similar. So the approximation here is quite good. The main difference is that the sort of zigzag on the thermal mass goes away and just becomes flat. So that's what the dynamics look like under the assumption where we just focus on the fast time scale. And then we can do a similar thing where we look only at the slow time scale. And we assume basically that changes in the indoor air temperature happen instantaneously. So we're doing this kind of quasi-steady state assumption on the indoor air. So here we get basically the exact thermal mass dynamics, no real change. The air temperature dynamics also look super similar between the truth and this model. In fact, I think they look basically exactly the same. But you'll notice that the energy or the power curve in the lower plot here actually looks somewhat different. And the main difference is that we have these spikes associated with trying to quickly increase the temperature of the indoor air. So when we do these step increases, bang, from 18 up to 21 Celsius, there's a ton of energy, needed basically to raise the temperature of that indoor air capacitance. And those spikes basically are washed out in the 2R2C model, where we assume only the slow dynamics matter. So we get the overall energy. If we look at the area under this curve, it's within 0.1% error. So it's essentially exact representation of what's happening in the 2R2C model. But if we looked at the peaks, for example, of this signal, we would see that there's quite a big difference between it. All right, so I'm going to stop there. We will kind of draw a little bit more on the 2R2C model and the two timing idea next lecture in order to draw an analogy between buildings and batteries, basically. And so, yeah, it's kind of cool material. I'm looking forward to that, but we'll get to that on Tuesday. So any questions about today's lecture? All right, well then while I have you for 2 more minutes, let me just pull up the MATLAB code for homework the next one. So here is basically these are the plots that your code should draw. One of them basically just, oh, I think I haven't updated my code here. So I will update it before I share it with you guys. But this is basically showing the weather data and then that exogenous thermal power data, the boundary conditions basically. And then you will draw one plot basically, which has to do with perfect set point tracking with saturation. So we get a very similar looking curve here to the ones that I just showed. And then the new one is basically the same boundary conditions, but you guys will implement the thermostatic control. So you'll see this kind of zigzag behavioral pattern where we don't track the indoor temperature exactly, but rather we're always kind of doing this sawtooth around it. So let me just walk through the code very quickly here. So again, we're in cell mode. If you expand these cells, you will find all sorts of comments and stuff like that from me. This basically is just introducing the script, setting some graphics similar to what we did in a previous one. This parameter or this cell here basically defines all the input data. And I don't think you have to put anything in here. I just want to draw your attention basically to the coding style. So our TA said that some of the code that she received from you guys on homework 1 was like really beautiful. And some of what she received was like academic spaghetti code, where everything is all in one line and nothing is commented, and the variable names are super weird and hard to interpret and stuff like that. So in order to make her life easier, but also in order to make your life easier, because it's easier to debug code that is written well, we will ask you to follow a similar programming style to the style that is in the MATLAB and the Python kind of starter code. So the basic idea there is that we use indentation, we use spaces, we try to use names that either match the equations that are in the slides or that are sort of human readable. And then basically every time you do something in code, you should have a comment that says a little bit of what you're doing. Maybe it's defining the variable that you just put in and expressing the units that it's in, or it's saying basically, the next 2 lines of code, here's what I'm trying to do conceptually. So that will make it easier for us to basically give you points on homework. This cell basically takes the input data and builds the system matrices. So this is more or less just looking at the slides and writing down the matrices. This code here defines the signal QE, the exogenous thermal power, based on these functions, which basically pull electricity usage data measured from some New York apartments and pull weather data for Lafayette kind of over this time span. And we plot that data. And then what you guys will do is fill in these functions for perfect set point tracking, which implements basically the decision of what the thermal energy should be that's supplied to the building, and also the dynamics. So you'll have to put in the 2R2C dynamics equations in order to basically calculate the temperature and the energy trajectories. And then this thing just plots those. And then you'll do the same thing. You'll create a function for implementing thermostatic control. So doing these kind of on-off decisions. And you can dig into these functions. They are fairly well commented. They talk about all the inputs and the outputs, the dimensions that they should be, and so on. And the length of the code that I've put in for the sort of your code here thing should reflect basically how many lines of code you need to actually do this. So your perfect tracking should be fairly few lines of code. Thermostatic control will take a little bit more logic, but probably no more than 10 or 20 lines of code. All right. So I will stop there. Thanks all for your attention, and we'll see you on Thursday.